Hey everyone, and welcome back for another deep dive. This time, we're going to be looking at a chemical process that's been absolutely crucial for over a century now, the Haber-Bosch process.
Yeah.
And especially for those of you out there in the world of chemistry and material science, especially at that graduate level, this one's got some fascinating nanoscience angles that you won't want to miss.
That's right. The Haber-Bosch process is how we synthesize ammonia, which is
Yeah.
the basis for the majority of fertilizers that we use and potentially a future fuel source. So quite a fascinating history and an equally fascinating future.
Okay, so let's unpack that history a little bit. So essentially, we're talking about a reaction that takes nitrogen from the air, combines it with hydrogen, and produces ammonia. Simple enough on paper.
Right.
But the real story here is the impact, right?
Absolutely. Back in the early 20th century, the world was facing a nitrogen shortage for agriculture. Natural nitrogen fixation just couldn't keep up with demand for food production. So the Haber-Bosch process was a revolutionary solution. It provided a way to synthesize ammonia on an industrial scale.
Yeah, it's really mind-blowing to think that this process developed over 100 years ago is still the backbone of how we feed the planet today.
Yeah.
But what makes it so challenging in the first place?
Well, the chemistry itself is quite straightforward. One molecule of nitrogen reacts with 3 molecules of hydrogen to yield 2 molecules of ammonia. But the catch lies in the nitrogen molecule. That triple bond between the nitrogen atoms is exceptionally strong, and in order to break it and get the reaction going, you need incredibly high temperatures and pressures. That's why Haber-Bosch plants are such massive, energy-intensive operations.
So we're talking about temperatures of 400 to 500 degrees Celsius and pressures hundreds of times higher than atmospheric pressure.
Yeah,
Not exactly a benchtop reaction.
exactly. So this is where catalysts come into play,
Right.
and specifically where the magic of nanotechnology really shines.
I think a lot of our listeners, especially those working on their masters or PhDs in chemistry and materials science, are already familiar with the role of catalysts. But for the uninitiated, can you break down why they're so crucial here?
Of course. So a catalyst essentially provides an alternative pathway for the reaction to occur, lowering the activation energy needed. In the case of the Haber-Bosch process, the catalyst facilitates the breaking of that stubborn nitrogen bond, making the reaction proceed at a much faster rate and under less extreme conditions.
Okay, and this is where the nanoscale comes in, right?
Exactly. By using nanocatalysts, we drastically increase the surface area available for the reaction to occur. So think of it this way. If you have a block of metal, only the atoms on the surface can participate in the reaction.
Yeah.
But if you take that same block and break it down into nanoparticles, you suddenly expose a huge number of new surface atoms, each capable of acting as a catalytic site.
So it's all about maximizing the bang for your buck in terms of active surface area.
Precisely.
Yeah.
And we're talking about particles smaller than 10 nanometers. At this scale, you start to see quantum effects and unique properties that you wouldn't observe in bulk materials. It's a whole new world of chemistry.
Okay, so nanocatalysts sound like the key to unlocking a more efficient Haber-Bosch process. What are the most common ones being used right now?
Well, the workhorse of the industry is still iron. It's relatively inexpensive and readily available, but ruthenium is another metal that's gaining traction, especially at lower temperatures. It is a bit pricier, though.
Yeah.
The research community is constantly exploring other metals, too, trying to find that perfect combination of activity, selectivity, and stability.
So it's like a constant search for the Goldilocks catalyst.
Exactly. And it's not just about the metal itself. The support material that the catalyst sits on and the promoters that are added to enhance its performance also play crucial roles. It's a complex puzzle.
Right.
And understanding the interplay between all of these components is key to designing better catalysts.
It sounds like there's a lot of exciting research happening in this area.
Yeah.
But before we dive deeper into the specifics of nanocatalyst design and development, let's talk about the elephant in the room, the environmental impact of the Haber-Bosch process.
Right. Yeah, while the Haber-Bosch process revolutionized agriculture, it's also a significant contributor to global greenhouse gas emissions.
Yeah.
Current estimates suggest it accounts for about 1 to 2% of global energy consumption and CO2 emissions.
Wow.
Not exactly a sustainable footprint.
Definitely a conundrum. We need ammonia to feed a growing population.
Yeah.
But the current production methods aren't doing the planet any favors.
Yeah.
What's the path forward?
Well, there's a lot of exciting research focused on greening the Haber-Bosch process,
Okay.
and nanocatalysts are once again playing a central role.
Okay, that's promising. What are some of the key areas researchers are exploring?
Well, one major area is the shift to renewable energy sources to power the process.
Right.
Imagine solar panels or wind turbines driving those high temperature, high pressure reactions instead of fossil fuels.
Yeah, that would be a huge leap forward in terms of reducing the carbon footprint.
Absolutely. And this ties in with another important strategy, finding alternative sources of hydrogen.
Right.
Right now, most hydrogen for Haber-Bosch comes from natural gas of fossil fuel. But what if we could use electrolysis powered by renewable energy to split water molecules into hydrogen and oxygen? That would give us green hydrogen ready to be used in a cleaner Haber-Bosch process.
So it's a two-pronged approach, clean energy to power the process and a clean source of hydrogen as the input.
Exactly.
But where do the nanocatalysts fit into all of this?
Nanocatalysts are crucial for making both of these strategies more efficient.
Okay.
Remember how we talked about their ability to increase surface area and provide more active sites for the reaction?
Right, more sites for the nitrogen and hydrogen molecules to interact and react.
Exactly. And by optimizing the design of these nanocatalysts, we can potentially lower the temperatures and pressures required for the Haber-Bosch process.
Yeah.
That translates to even less energy consumption overall.
That makes a lot of sense. So we're not just talking about greener inputs, but also about making the process itself inherently more efficient. Are there any specific examples of how researchers are pushing the boundaries of nanocatalyst design in this context?
Absolutely. One exciting frontier is the development of single-atom catalysts.
Okay.
These are catalysts where literally every single atom is involved in the reaction. It's the ultimate in atomic efficiency.
That sounds incredible. How do you even go about creating a catalyst with individual atoms?
It requires very sophisticated techniques, often involving anchoring individual metal atoms like ruthenium onto carefully engineered supports like graphene sheets or metal oxides.
Right.
The goal is to isolate these atoms and prevent them from clumping together.
I imagine this kind of research is at the cutting edge of material science.
It absolutely is, and single-atom catalysts are showing great promise for ammonia synthesis at lower temperatures and pressures.
That's remarkable. Are there other nanocatalyst designs that are being explored for green ammonia production?
Definitely, bimetallic nanoparticles, for example, combine two different metals at the nanoscale, often offering enhanced activity and stability compared to single metal catalysts.
Yeah.
And then there are core shell structures where a nanoparticle core is coated with a thin layer of another material. This can be a way to protect a highly active but less stable core, or to fine-tune the catalyst's properties.
So it seems like researchers are using the entire nanotechnology toolkit to find innovative solutions for green ammonia production. But I'm curious, are there approaches being explored that go beyond tweaking the traditional Haber-Bosch process altogether?
Yes, scientists are always pushing boundaries. One intriguing alternative is electrocatalytic synthesis, which uses electricity to directly convert nitrogen and water into ammonia.
Wow.
This method bypasses the need for separate hydrogen production.
That sounds remarkably efficient and potentially a perfect fit for renewable energy sources.
Exactly. And then there's photocatalytic synthesis, which uses sunlight to drive the reaction that's the ultimate green energy source, right?
Absolutely. It seems like there's a whole spectrum of innovative approaches on the horizon. But before we get too carried away with the possibilities, it's important to acknowledge that there are still challenges to overcome.
You're right. Scaling up these green ammonia technologies to an industrial level will require significant investment, and continued research and development issues like catalyst stability and durability in real-world conditions are also critical.
Right.
And of course, we need to ensure that these green alternatives are economically viable.
Yeah, those are all important considerations.
Yeah.
But despite these challenges, it sounds like the field of green ammonia production is incredibly dynamic and full of potential.
It definitely is. The scientific community is fully committed to finding sustainable solutions for this vital process.
Well, I'm feeling optimistic after learning about all these advancements. It's exciting to see how nanotechnology is playing such a pivotal role in shaping a more sustainable future for ammonia production. But before we wrap up, I want to touch on another aspect of green ammonia that we haven't discussed yet: its potential beyond fertilizer production.
That's a great point. Green ammonia has the potential to be a game changer in a variety of sectors, particularly as a carbon-free energy carrier.
Okay, let's dive into that. We mentioned ammonia as a potential fuel source earlier. Can you elaborate on that?
Sure, ammonia has a higher energy density than hydrogen, making it easier to store and transport. It can be used directly in fuel cells or combusted in engines. Imagine a future where ships, planes, and even entire communities are powered by green ammonia.
That sounds like a truly transformative vision. It seems like green ammonia has the potential to revolutionize not just agriculture, but also the entire energy landscape.
Exactly. And as we continue to develop and refine these green ammonia technologies, we are opening up a world of possibilities for a more sustainable future.
This has been an incredibly insightful conversation. It's clear that the research happening in the field of green ammonia is not just about groundbreaking science, but also about a deep commitment to a more sustainable and equitable future.
I couldn't agree more.
And on that hopeful note, we'll wrap up this part of our deep dive into the Haber-Bosch process and the exciting world of green ammonia. But don't go anywhere just yet. In Part 3, we'll shift our focus to explore some of the cutting-edge research happening right here in our own labs, focusing on the development of novel nanocatalysts for sustainable ammonia synthesis. Stay tuned. Welcome back to the final part of our deep dive into the Haber-Bosch process and the quest for green ammonia. We've covered a lot of ground, from the history and the challenges of this vital process to the exciting advancements in nanocatalysis that are paving the way for a more sustainable future. Now let's bring it home and talk about the groundbreaking research happening right here in our own labs.
Yeah, what's particularly exciting is our focus on developing novel nanocatalysts specifically designed for sustainable ammonia synthesis. We're talking about pushing the boundaries of material science to create catalysts that can operate under milder conditions, maximize efficiency, and minimize environmental impact.
I think our listeners, especially those in the thick of their graduate studies in chemistry and material science, would love to hear about the specific types of nanocatalysts you're working on. What's at the forefront of your research?
Well, one area we're really excited about is single-atom catalysts. As we discussed earlier, these offer the ultimate in atomic efficiency, with every single atom actively participating in the reaction we're exploring. A range of metals, from ruthenium to platinum, and even iron anchored onto meticulously engineered supports like graphene or metal oxides.
It's fascinating to think about a catalyst where every atom is a player in the game, but I imagine creating these single-atom catalysts is incredibly challenging. What are some of the hurdles you face in the lab?
It's definitely a delicate dance. We need incredibly precise synthesis techniques and advanced characterization tools to ensure we're actually creating isolated single atoms and preventing them from clumping together. Techniques like atomic layer deposition and electron microscopy are essential for controlling the size and distribution of these atoms on the support material.
So you're essentially working at the atomic level, manipulating matter with incredible precision. That's quite remarkable. But why go to all this trouble to create single-atom catalysts? What are the advantages over traditional nanoparticle catalysts?
Well, there are several key advantages. First, by using single atoms, we can maximize the use of precious metals, which are often expensive and limited in supply. And second, single atom catalysts often exhibit unique electronic properties and catalytic activities that differ from their nanoparticle counterparts.
So you're not just improving efficiency, but potentially unlocking entirely new ways to catalyze the reaction.
Exactly. It opens up a whole new realm of possibilities. And we're also exploring ways to fine-tune the electronic properties of these catalysts by carefully selecting the support material and manipulating its structure. It's all about creating the ideal environment for the nitrogen and hydrogen molecules to interact.
It sounds like a delicate balance of chemistry and material science, optimizing every aspect of the catalyst to achieve the desired performance.
Absolutely. And our research isn't limited to single-atom catalysts. We're also investigating other nanostructures like bimetallic nanoparticles and core shell structures.
Can you give us a quick rundown of those?
Of course, bimetallic nanoparticles combine two different metals, such as iron and cobalt, at the nanoscale. And this can lead to synergistic effects where the combination is more active and stable than either metal alone.
So it's like a tag team effort with each metal bringing its own strengths to the table.
That's a great way to put it. And then there are core shell structures where a nanoparticle core is encased in a thin layer of another material. This can be a strategy to protect a highly active but less stable core, or to tailor the catalyst's properties by controlling the interaction between the core and the shell.
It sounds like you're exploring the full spectrum of nanotechnology to design these next-generation catalysts. But I imagine it's not just about designing them right. You need to put them to the test as well.
Absolutely. We have state-of-the-art facilities where we can test these catalysts under realistic reaction conditions. We can measure their activity, selectivity, and stability, and use that data to further refine their design. It's an iterative process, constantly tweaking and improving.
Yeah, it's a testament to the power of scientific inquiry, this constant cycle of designing, testing, and refining. And I'm sure it's incredibly rewarding to be at the forefront of this research, knowing that your work could have a real-world impact on such a critical process.
It's truly inspiring to be a part of this effort, and it's not just about improving the efficiency of ammonia production. It's about developing sustainable solutions that will benefit both the planet and future generations.
That's a powerful message, and it brings us full circle to the broader vision of green ammonia and its potential beyond fertilizers. What are some of the specific applications that your research could contribute to?
Well, imagine a future where farmers can produce their own green ammonia on-site using small-scale reactors powered by renewable energy sources that would decentralize production, reduce transportation costs and emissions, and create a more resilient agricultural system.
That's a compelling vision of sustainable agriculture. What about applications beyond farming?
Green ammonia could also play a vital role in decarbonizing heavy industries like shipping, which currently rely heavily on fossil fuels. It could be used to store energy generated from intermittent renewable sources like solar and wind power, helping to create a more stable and reliable energy grid. The possibilities are vast.
It's truly exciting to see how green ammonia has the potential to transform not just one industry, but entire sectors of our economy, moving us toward a more sustainable future.
And that's what makes this research so compelling. It's not just about advancing scientific knowledge, but about applying that knowledge to solve real-world challenges and create a better world.
Well said. And for all of our listeners out there, especially those future chemists and material scientists working hard in their labs and classrooms, remember that your passion and dedication can make a real difference. The future of sustainable chemistry is in your hands.
Absolutely. Keep exploring, keep innovating, and never stop asking questions. That's the heart of scientific discovery.
That's a fantastic note to end on. Thanks for joining us on this deep dive into the world of the Haber-Bosch process and the exciting future of green ammonia. Until next time, keep those brains buzzing.